got about 3 minutes after, and might as well go ahead and get started. We'll probably have people hopping on here for the next few minutes. This webinar is for effective energy modeling strategies for geothermal systems, and it's sponsored by Groundwork Design Software and the GeoTrainer Group. This is the third in a series of monthly webinars that we're running for geothermal professionals, and it's intended to help promote our geothermal industry. I'd like to remind everyone that we're not presenting this as a substitute for doing formal training, and we encourage everyone to be in programs such as to use training for your tools like. Today's presenter is Ed Lorenz, and let me tell you a little bit about Ed. He's worked in the industry since the 80s as a residential system designer and installer, ground source heat pump equipment distributor in Canada. And in 1984, Ed began looking into integrated geothermal ice rink and ice storage systems, and is now recognized as one of the most experienced low temperature heat pump experts in the industry. And between residential and commercial projects, has well over 10,000 tons of heat pump capacity operating throughout North America and Asia that he's directly designed or consulted on. Ed's an accredited installer and trainer for IGSPA. He's a certified GeoExchange designer, member of ASHRAE. He's taught for the GeoExchange Coalition in Canada, and he's trained hundreds of contractors and engineers through IGSPA, the CGC, and other field training classes. Ed is the founder and current president of GeoExergy Systems, and he provides consulting service to both end user clients, mechanical engineers, and architects and others in the GeoExchange industry. So Ed's got a wealth of knowledge about the topic, and I encourage any of you that have questions to jot them down. At the end of the session here, we'll probably have about 20 minutes available for doing Q&A. And in the meantime, also, if we could ask, please mute your mics, make sure the background noise on your end doesn't come through. So with that, I'm going to turn it over to Ed. Ed, good afternoon, good morning. Actually, I think Ed's got his mic muted here.
Okay, that's better? Okay, there we go. What I'll be talking about today basically is sort of the first steps in the design process for that we use for geothermal system design. For basically, we do a lot of commercial system, larger commercial system design, and it really there is a process involved in this, and if we follow a basic process on this, it makes the design of a system a lot easier and a lot more understandable. What we found over the years is that when a client comes to us, basically they typically ask us a couple of questions. What's it going to cost us to build a system? You know, basically why should we do it? And what's it going to save us? They want to basically justify the cost of putting a system in. It really doesn't, what we've noticed is it really doesn't matter how green the client professes to be. If they can't get a return on their investment, they don't get the green, and this is what they're really after. If somebody's looking for a system and they expect 3 or 5 or 7 year payback, then generally they'll accept that and go with it. If it's going to be a 25-year payback, it's probably not going to happen. So basically, what I'll do is go through the process, and that we typically follow, and it seems to work well for us. What we found is that if you've got a client coming in the door, basically they're presenting you 2 givens. The site, the land area that you've got available, is a given. It's not going to change in most cases. And the geology certainly isn't going to change. It is what it is, and that's what you have to deal with on that site. And that's going to be different on the next site, and things are going to change because of it. But what you can change, however, is the architecture of the building, the design of the building, and the mechanical systems that are in the building. Those you can have a large impact on, And with good energy modeling, you can have a really fairly good estimate of how different changes in the building, the glass, the lighting, the whole bunch of things in the building can have an impact on the size of the ground heat exchanger. So basically, where we start basically is with as detailed as an energy model as we can develop, working as early in the process as possible with the architect, the owner, the mechanical system designers, and then we can provide answers for the client as to the two questions that they have: what's it going to cost, what's it going to save, and we can also have a fairly high level of comfort in the design that we're building. So basically, if somebody comes in with wants a conventional boiler cooling tower system, you're connecting up to a grid that it doesn't matter how much energy you take out, whether you run the system for 10 hours a year or 10,000, or 8,000 hours a year. It doesn't matter. As long as somebody is paying the energy bill, you have access to that energy. And same with a cooling tower. Basically, if you've got you're specifying a cooling tower out of a catalog, and you know that if you selected the cooling tower properly, you're going to be getting that kind of performance out of that cooling tower on the hottest day of the year. And other than that, nothing really matters. Design process basically is fairly simple for a conventional system. You need to look at what the peak heat loss is of that building, and what the peak heat gain is of that building. And then you can select the equipment, design the system, prepare the specifications and drawings, build the system, and then you can design the system. You don't have to worry about you only have to worry about how big that gas line has to be to deliver the BTUs on the hottest and the coldest day of the winter. When you're looking at a geothermal system, you're not connected to the grid, and you're not specifying a cooling tower or the catalog. What you're doing basically is designing the energy source. So, somebody else is designing the energy source if you're connecting to a gas system, somebody in Texas or Oklahoma or Alberta or wherever. But here, you're responsible for not only the mechanical system design, but how big a piece of dirt you have to touch to be able to get the energy loads that you need. That means you need to understand both the peak heating and cooling loads, as well as the monthly energy loads. How much energy you're going to take out of the ground every month, how much energy you're going to put back every month. And then if you're, where you can have a lot of influence on how big that ground heat exchanger has to be, is to try and get a reasonable balance on the amount of heat you're dumping into the ground and how much heat you're pulling out of the ground. That's a lot more work than you're going to run into with a conventional system where you're connecting up to the grid. It's kind of like if you were designing a system up in northern Alaska or up in northern Canada, basically, you'd be looking at getting energy delivered by barge or by ship once a year, and you have to design the storage tank that goes with it. You want to make sure that the storage tank is big enough to last you the whole year. And then you have to know how much energy you're going to be taking out on a monthly or daily basis, and design the system, the size of the system accordingly. The peak, you have to understand the peaks to be able to heat that building on the coldest day of the winter. But you have to make sure that you've got energy all the way through till the following summer. So the design process is this is the design process that we've basically developed. So if a client comes in the door, basically you've got to understand how much energy you're gonna need. We're basically starting with the building energy model.
And you have Russell.
Okay, okay, that's better. You're looking at you can have an influence on the building. You need to know how much energy you have to pull out of the building or dump into put into the building, and you can have an impact by looking at the building design itself, the mechanical system, and then you also have to deal with the geology, which is a given. And at that point, once you've looked at how much energy you need to pull out of the ground, you can basically look at the land area that you've got available and determine what kind of ground heat exchanger you can put on the site. How much room do you have? You can get a decent estimate basically to find out, you do some calculations to determine how big that ground heat exchanger has to be, how much pipe you have to put in the ground. So basically, at that point, you can get a reasonably good estimate of how big and how expensive that ground heat exchanger is going to be. That answers one of the questions for the client. Once you have the energy model as well, then you can translate the number of BTUs that you're pulling out of the ground or dumping into the ground, or that you have to put into the building, into energy costs based on the utility rates in that area. So that answers basically at this point the two questions that most clients are going to ask. And if the number isn't acceptable, then they will often go with a conventional HVAC system. If you're looking at a 20 or 30-year payback, most clients aren't going to buy that. What we can do at that point is go back through the process again, work with the architect, work with the owner, and see what we can do with hybrid options, see what we can do with the design of the building or the mechanical system, and go through the loads once again, change the energy load. Once we've done that, then we can determine, use that, conduct a thermal conductivity test, and determine whether the assumptions that we made in our preliminary model of the ground heat exchanger were reasonably accurate or not. And basically what we're doing is confirming that our assumptions are accurate. And again, at that point, if the numbers turn out to be not very good, the client can go down with the conventional system, but at least then he's got a good energy model to start with. Or we can look at other options, a hybrid gas boiler, for example, as auxiliary, or add a cooling tower to the system, or some other devices that can help balance the load. Once we've got past that stage, then we can design the system, and then it becomes like designing a conventional system. What you're doing is communicating your ideas to the client as best you can with the specifications and drawings. Then you're looking at implementing a system, make sure that the system is being installed properly and commissioned properly. And then this is becoming a bigger issue. We're finding this has become a bigger issue as well, is making sure that the operator, the building owner, understands what they've got and what they should expect from the ground heat exchanger. So basically, this is an iterative process. We'll go through, often on a lot of buildings, we'll go through about half a dozen to a dozen different energy models and go through the ground loop design software, or use some kind of ground loop design software to get an estimate of how much pipe we have to put in the ground based on that energy model. And we can see fairly quickly, if we change this, if we change that, if we do this, if we do that, then what's the effect going to be on the size of the ground loop and the cost of the ground loop and the energy cost for the system. So basically, we'll go through a building probably half a dozen times, working in basically a really well integrated design process, and till we finally get to the point where we can justify the cost that we're asking the client to spend. So today, basically, what we're looking at are looking at the building and looking at the mechanical system, and how can we have an impact on both of those things to really optimize the size of the ground loop and optimize the efficiency of the system. I'll go over a quick couple of examples of why the energy loads are so important. These are three buildings, three hypothetical buildings: a church, a retail store, and a multifamily residential building. On each one of these, the peak cooling load is identical, 497,000 BTUs per hour. The peak heating load is also identical, 385. Okay, so those are identical. And a lot of rules of thumb that have been developed in the geothermal industry basically say you need so many feet per ton of drilling, so many feet of drilling per ton of equipment, or you need so many watts per meter of borehole, whatever it is. And that's why you can get yourself into trouble if you're using standard rules of thumb like that, because the size of the ground loop is going to differ quite a bit depending on how much each of those systems is going to run over the year. In other words, how much energy you're shoving into the ground or how much energy you're pulling out of it. So if we look at the church, again, remember that each of the peak loads on each of these buildings is identical. The church is used typically only a few hours during the week. Lighting levels are typically fairly low. There's not much going on in the building. There's often not a lot of windows in the building. Low internal gains, and we end up with, in this case, if we're looking at the ground-up design software, basically with those kinds of loads, we're looking at requiring about 8,300 feet of drilling, and that would be to meet the heating loads of the building, and we can easily meet the cooling loads with about 6,600 feet of drilling. And then we can see what happens to that ground loop over the longer term. This is a relatively balanced ground loop, slightly heating dominant. The temperature would probably drop a few degrees over 20 years. If we look at a retail store, that kind of a building, even though it's got identical peak loads to the church, is run very much differently. The retail store, a typical store is going to run 12, 14, 16 hours a day. Some stores 24 hours. There's a lot of lighting in there, a lot of people in there to generate a lot of heat that is not needed to be taken from the ground heat exchanger. In fact, you're going to be shoving heat into the ground heat exchanger in a lot of these buildings much of the winter. So basically, that's going to change what the size of the ground heat exchanger is. In this case, also we're up to 8,800 feet of drilling required for cooling this time, not for heating, but for cooling. And what we need for heating is a lot less. The ground heat exchanger is about 7% bigger than what we need for the church. The way it's going to run over the long term, even though we've got 7% more drilling, that ground loop temperature is going to rise over time. So we want to be careful, depending on, and there may be other influences such as aquifers or water that's flowing through that may not make this quite as bad, but the temperature is still going to go up and it's going to operate less efficiently in cooling. We take again the same maximum heating and cooling loads, but apply it to a residential building. That's going to operate differently again. Different lighting loads, different occupancies. What that does in this building, we can look at this very quickly, looking at 7,700 feet of drilling instead of 8,900. And one thing to notice here is that the amount of drilling that you need for cooling on this in this building is very close to the same amount of drilling you need for the heating. In other words, the loads are fairly balanced. What that means again is that it changes the long-term temperature profile of that ground heat exchanger. Here's the store. Here's the church. Here's the residential building. So the loads are going to have a large impact on how efficiently that system is going to operate over the long term, and how expensive it's going to be to build it. So if we look at the energy balance is a fairly big deal. These are the building loads itself. Here's how much heat we have to extract from these buildings. You can see how much different they are. This is the annual energy loads. Here's how much heat we have to supply to the building. Then we also have to consider, and this is where the software the software is very useful, looking at what we can very quickly look at how large that ground heat exchanger has to be, and we have to look at the efficiency of the equipment that we're putting in there. Then we can come up with what's actually going into, how much energy we're actually putting into the ground, and how much energy we're actually pulling from the ground. In this case, the building loads are about 70,000 or 700,000 BTUs per hour, and what's actually going to be extracted from the ground is a bit over 500,000 BTUs per hour. Quite a bit different. The compressors are going to supply the rest of this heat. Same in the cooling load. If we look at the cooling load here, the building needs about 800,000 BTUs or 800 kBTUs over the year, but it's actually going to dump close to 1 million kBTUs into the ground over the year. What that does to the ground heat exchanger itself is the number of feet of drilling that we need. This is for the church, a bit over about 8,300. This is for the retail store. We're at almost 9,000. Here we're about 7,700 for the multifamily. You see that the building that is more balanced is actually going to have the shortest ground load, even though the peak heating loads and the peak cooling loads are identical. there's about a 15% difference in the length amount of drilling that you're going to need between the retail and the multifamily. So if we look at some of the things that we can do with the building, working with the architect and the owner to change things on the building. This is where it's critical to work with the architect as early in the process as you can. Look at what the energy model is going to be, model it as accurately as you possibly can, and then you can provide the answers that the client is going to need, the energy cost and the construction cost, so they can calculate what their return on the investment is. Energy model is the single most powerful design tool that you can use for designing a solid ground heat exchanger that's going to work over the long term. There's nothing else that's going to compare to that. And then using good grounded design software, you can see what the impact is of the energy model, changes to the energy model, what that's going to do. So building construction details, there's a lot of things that you can look at. Shading on the building, how much solar again you're going to get, what kind of roof is going to be put on, white roof or green roof or whatever, what the plug loads are going to be in the building, what kind of equipment is going to be in there, lighting, occupancy, glass specifications. Those are all things that can have a very major impact on how large and how expensive that ground load is going to be and how efficiently that building is going to operate. If we look at different roof options, you can what we're typically seeing is that we can reduce the cooling loads, both the annual energy loads as well as the peak loads, by 10–15%, give or take a little bit. And that can have a big impact on the size of the ground load. In a lot of cases, you'll see that if you can reduce the size of the ground load by 15%, you can pay for an awful lot of better roof or other features in the building. Things like lighting options, like retail stores, for example, are typically will look at about 2.5 to 3.5, even up to 4 watts per square foot. LED lighting can reduce that by down to as much as 1 or 1.5 watts a square foot. And if you're looking at, let's say, a 100,000 square foot building, you can knock 100 kilowatts or about 300,000 BTUs, or about 25 tons or so, off the size of the ground, off the size of the equipment that you need for the building, and that's going to have a big impact on the size of the ground heat exchanger as well. So it's a big deal. Daylighting, how much you need to use the lighting can be impacted by things like the solar tubes, light shelves, that kind of thing. With detailed energy modeling, looking at it in detail, and you have to look at these things in enough detail to really see what the impact is. Some of the changes that you may not think of having a large impact can have a fairly major impact. Things like lighting level sensors. You can see that the lights in these areas are basically shut off, and you supply the light where you need it, when you need it. There's no point in putting these lights on, dumping heat into the building all day long if you are getting enough light just from the windows. As the lighting levels outside change, you can bring the lights on. Those kinds of controls, you may see that spending 20 grand on lighting controls will save you $30,000 or $40,000 on the ground heat exchanger. Lighting occupancy sensors can make a big deal. People often don't shut off the lights when they should be, and the lights in the boardroom may be on all day long if there's a meeting at 9 o'clock in the morning. If there's an occupancy sensor, they'll be shut off automatically. Solar shading, that can have a huge impact, and working with the architect, in this case you'd have to work directly with the architect and look at what the impact is of shading. It may be very worthwhile looking at this kind of shading or shading controls on the building to and justify it simply by the cost of the ground heat exchanger, but seeing what the impact is on the cost of the ground heat exchanger and what the impact is on the efficiency of the system. With a good energy model, you can predict with reasonable accuracy what the energy cost is going to be. Operating windows, again, a bit more challenging to model accurately, but they will have an impact on the cooling loads. Glass is another big thing on a building. Looking at what simply specifying glass that's this shade of blue is simply not adequate. You can look at what the shading factor is and show the architect or the building owner that if you put in this kind of glass you are going to have an impact on, this is what it's going to cost you to operate the building, this is what's going to cost you to build the ground heat exchanger. So they may be able to put in better glass and justify it if they're putting in the right kind of glass. And sometimes it's challenging to get the glass specifications from the architect. You have to dig around for it sometimes, but the more accurate you can make those models, the better it's going to be. We've seen building cooling loads be reduced by as much as 20 to 35% in some buildings, which can have a huge impact. In a lot of cases, they can make enough difference so that you actually have room on the site to be able to install a ground heat exchanger. Electronically tintable glass is becoming available with really good shading factors, and that's going to make a difference. Again, it may be something that's going to provide better levels of comfort in the building, as well as when you look at the whole picture, the cost of the glass and the ground heat exchanger may easily justify the cost of the better glass. So if we also look at the mechanical system, there's a lot of impact that you can make on simply by how the mechanical system is designed and what type of system is going in there. One of the big things basically is, again, you really need to understand that the ground heat exchanger is an integral part of the mechanical system. It's not just something that's added to it or not something that you can specify out of a catalog somewhere. Looking at a ventilation area, how do you handle a ventilation area to the building is a fairly big deal. If you're looking at a northern climate or a southern climate, it can be a really big deal. Adding heat recovery ventilation to this building dropped the heating energy loads by about 15%. If you're looking at, you can look at using gas rooftop units, for example, or heat recovery ventilation or energy recovery ventilation. In some cases, you may want to be, especially in northern climates, in order to balance the loads, it may be better to put in a gas rooftop unit rather than a gas boiler to supplement the system. And you can often make a building that would be normally heating dominant if you tried to do this with a geothermal system. Turn that into a cooling dominant building even in a fairly northern climate. And then use this as much as you need to. Sometimes, in some cases, you can actually put a hydronic coil in parallel with or in series with the gas rooftop unit and use that to help balance the loads as the system operates from year to year. A lot of cases using outdoor air, cool outdoor air to cool a building itself. An economizer basically can reduce the annual energy loads. It's not going to do anything to reduce the peak loads, but it certainly can reduce the annual energy loads. If you look at a building without an economizer and a building with, you can eliminate the cooling load, annual cooling load, in the winter and spring and fall months, whereas here you'd be using the system and dumping heat into the ground. And you need to look at what the energy balance is of the whole building and see if it's worthwhile doing that or if it's or not. The impact made on this specific building is about 5,000 feet of drilling, or 5,500 feet of drilling. Cost of $14 per foot, $60,000, 12 fewer boreholes that you need to find room on the site for. 16% reduction in the use of the ground. The other thing that kind of thing does is it can be used to help balance the annual heating, cooling energy to the ground. If you've got an unbalanced building, that ground loop is going to get a lot warmer than if you use the economizer. This one rises from 60 degrees the first year up to about 90 degrees by the end of 20 years. Here we're looking at 60 degrees up to 75 degrees. The efficiency over the long term is going to be a lot different. Looking at CO2 sensors to control the amount of ventilation air that you need for the building can have a big impact. You can see that the peak loads are reduced a bit, and the annual energy loads are reduced to some extent as well. You can see the big impact on the amount of heat that you need to supply to this building. This is in a more northern climate, so it's going to have an impact for sure. In this case, the amount of drilling that you needed for this building, if you just supply the fresh air directly to the building, or if you use a heat recovery ventilation system, or if you use the CO2 sensors to control the amount of ventilation air that you need. There's a huge difference from 26,000 feet of drilling down to 16,000 feet of drilling, and down quite a ways if you're using a heat recovery ventilation system. CO2 sensors may not be the appropriate control in all buildings, but if you're running let's say a retail store that has 30 or 40 customers in it first thing in the morning till about 11 or 12 o'clock, and then you get an influx of people over lunch, you can supply the CO2 during that time when they need it, and then basically reduce the amount of pressure that you need to introduce quite a lot for the rest of the day. That can have an impact again on what that ground loop is going to do over the long term, and using software like this to predict that can give you a lot better, higher level of comfort that that system is going to operate well over the long term, or not. Then you, or would you have to should be looking at doing something else to try and get a higher level of comfort that that system is going to work. We talked a little bit about the efficiency of the equipment, how the equipment is selected, and with the ground loop design software, basically, you can select the operating parameters of the building. The default would be typically to supply, in order to supply about 45-degree chilled water to the building, we'd have water coming to the heat pump at about 55 degrees. And to supply 105 or 110 degrees to the building, to the air handlers, we'd have to have a return temperature of about 100 degrees. We can change those parameters, but then we're looking at, and we can do that, we would do that when we're looking at, let's say, radiant floor cooling, for example, and radiant floor heating. We can operate much different parameters than with an air handler. Here we're looking at 77 degrees versus 55. Here we're supplying 45-degree water to the building. Here we're supplying about 66 or 68-degree water to the building. Here we're supplying maybe 90-degree water to the building. Here we're supplying 110. What that does is change the efficiency of the equipment, changes the capacity of the equipment, and more importantly, it changes how much pipe you need to put in the dirt. We're looking at knocking off over, about 14% of the cost of the ground loop by changing the distribution system. We look at the efficiency on the equipment. We're looking at this line here is basically what the COP is. If we've got a 100-degree temperature difference between the ground loop and the building's supply temperature versus, let's say, a 50-degree temperature difference, here we could be operating at supplying 130-degree water to the building, and with a 30-degree ground loop. Here we would be looking at 50 degrees. We'd be looking at, let's say, 35-degree ground loop and providing 85-degree to the building. There's a huge difference in what the COP is. Here we're looking at a COP of just over 2. Here we're looking at a COP of 4.3 or 4.4. That's a huge difference. Looking at what the heating capacity is, that changes from about 100,000 BTUs up to about 105 or 107,000 per heat pump. And it in some cases can reduce the amount of equipment that you need to put in the building. COP, again, right from looking at the manufacturer's specification, COP of 3.2 versus 2.4. That's a fairly big deal, simply by changing the temperature that you're designing a system to operate at. You do have to consider the distribution system. If you're looking at supplying 120 degrees, you can look at a smaller fan coil unit than if you were supplying, let's say, 100-degree water. You have to be aware of the implications of what you're doing when you're making these kinds of changes, and it will have an effect on how much water you have to supply, deliver to each of these fan coils, the piping size and things like that. But yeah, and you have to look at the overall picture. But it can make a huge difference on how efficiently that system is going to operate. If you're doing a radiant floor system like this in concrete can supply about 15 BTUs per hour per square foot with 100-degree water temperature. Here it's 120-degree water temperature, COP drops to 2.7. 130 degrees drops down to 2.4. If you're putting it under a floor, for example, and you need 145-degree water to deliver 15 BTUs per square foot, your COP drops by a pretty dramatic amount, down to about 2. And you're going to need to supply 145 degrees you're going to be looking at much higher compression ratio on the compressors. It's going to make a difference on how long the compressor and that is going to last as well. So basically, those are some of the things that that we will look at when we're doing a system design, looking at the what the building is, how we can make changes to the building or the mechanical system to have an impact on the whole rest of the system. So basically, that's sort of a introduction to a lot of things that we go over in the full Certified GeoExchange Designer course, this is the same process that we use in our company basically to design some of the systems that we do. So I've gone through all the material. If you have any questions, I'll be around here for a bit. Please feel free to ask questions or whatever. Appreciate your time. Thank you. So if there's any questions, I'll be around here for a bit.
Ed, I have a question.
Okay.
I'm Dan.
Okay.
So when you're looking at the whole geothermal design process for a building, and you think about the amount of time you spent on, the ground loop design, the amount of time you spend on the, the energy model, et cetera, what percentage of your overall design time would you say is spent on the energy model?
I would guess probably that's about half of our time, 40–50% of our time. And working, we try and get into the design process as early as we can with the architect, with the owner, with the full design team. Then, like a design charrette is a very good place to start this process. We've remember one building that we looked at where the electrical engineer presented what the cost of putting in high efficiency lighting in the building was. It was going to cost about $1.25 a square foot, about $500,000 on the building that we were looking at. They were running at about 2.5 watts a square foot is what they were for the system they were proposing, and we knew that by putting in more efficient lighting, it could drop that by about 50%, or about 400 kilowatts, or about close to 1 million BTUs per hour. That was a big deal on that. That reduced the size of the ground heat exchanger and the cost of the ground heat exchanger by about $600,000. So in other words, by putting in high efficiency lighting, they would save $100,000 on the cost of the lighting and the ground loop. So that's why I'm saying it's a very important aspect of the whole design process. This is where in this area is where you're building the full basis of design of the system. You're looking at what kind of mechanical system you're going to be putting in. Is it going to be an air handler system? Is it going to be a radiant floor system? Or what is it going to be? And that's at that point you're making those kinds of selections. You've got to look at a fair bit more work at this point. You should certainly be charging more for your time because you're doing a lot more. The rest of this becomes once you've done that, you're looking at maybe a little bit of time for confirming your assumptions that you've made at this point. Once you're at this point, you're simply putting the design that you've developed, the basis of design that you've developed here. You're communicating that to the contractors or to the owner, and then it's a matter of making sure it's being installed properly and then operated properly.
Ed, a follow-up question. Do you ever get pushback from some of the partner firms that you're working with on these? Like you say, we really need to do an energy model and this is how much it's going to cost. Do other people sort of say, we don't want to pay for that? And how do you deal with that, if that happens?
Basically, what we try and do is we'll do an energy model, and where we get pushback from, let's say if we're working for an engineering firm that hasn't done a geothermal system design before, we'll often look at doing but they've asked us to do the ground heat exchanger design, and we may not even tell them that we're actually doing a detailed energy model like we are, but then we can show them and show the client that if you do this, this is what the impact is. Here's what if you change this on the design, this is what the impact is. If you change the type of how you're doing, what temperature, distribution temperature you're supplying to the building, here's what the impact is. If you can show them the real numbers with a fair bit of confidence that these are the numbers, here's what the impact is on energy efficiency, here's what the impact is on the cost, which is what the client wants to hear, then then you can really start getting some buy-in from both the client and from the rest of the design team. It's a matter of understanding why you need this and why the energy models are so important. We've done a lot of work for some engineering firms where when they're doing a ground loop design, they're calling us earlier and earlier in the process. Okay, so how do we do this? And again, we're teaching them at some point, and eventually they're going to learn how to do it on their own, but at least then they are doing it properly. I had one question about using the ground loop design software to use a coaxial heat exchanger. Dan, do you have any comments on that?
We're planning on adding that functionality into an upcoming release of the software. But what I've seen is they typically reduce the ground loop lengths approximately equivalently to a W bend. So if you're trying to get by with a best guesstimation, the W bend is one approach. Ed, what do you think?
Yeah, I think what you're changing is really the borehole thermal resistance on the heat exchanger. Adding more pipe, you're basically adding more heat exchange surface by putting in a coaxial heat exchanger. It's not going to change the thermal conductivity of the ground. It's not going to change the amount of energy that you're trying to shove into the ground. The ground can only take so much energy, and putting a bit more heat exchanger is going to get it into that mass of dirt a little more quickly than if you had just a single U-bend in there. But it's not going to change the amount of energy, the length of the ground loop by a whole lot. I think basically, and you can model that in GLD by basically manually changing the borehole thermal resistance of the U-tube. That's probably the best way to do that.
Yeah, and Ed, if you don't mind me sort of chiming in here,
yep.
The best way to reduce your drilling requirements is to get your energy modeling right, such that you can figure out how to balance your heating and cooling loads that are going into and out of the ground. When you can figure that out, that's like the best way to ultimately reduce your installation costs for your loop field.
Yeah, the one, like I said earlier, the most important thing in ground loop design to make it as a designer, you want to do two things. You want to design a system for the client, but the client is almost invariably, I think I've had 2 clients in 30 years that haven't asked this question, that it hasn't mattered. It's energy cost. What's it going to save me? What's it going to cost me? They're looking for what the return on their investment is. Why should they spend the extra money doing this? They want to be green, but they're not going to spend a huge ton of green to be able to get there. The 2 most important things where we've been able to reduce the size of ground loops, and we've done that. We reduced the size of ground loops by as much as 40, 50, in some cases even up to 60% by going through this process, building a detailed energy model of the building and the mechanical system that's going to be going in there, and then we found out we can improve the efficiency. We can reduce the energy cost for the building, and we can reduce the cost of building the system in the first place. We can have a huge amount of impact by doing these 2 things. We can't do much with this. It is what it is. We can start doing some things depending on how much land area we've got by looking at hybrid options with gas auxiliary boilers, auxiliary cooling towers, or whatever else. But where we can have the single biggest impact is this. We can have virtually no impact on here except by have minor impacts on the design, the detailed design of the ground heat exchanger with borehole spacing, high thermal conductivity grout, things like that. Changing the diameter of the borehole, adding an extra U-tube, putting coaxial heat exchangers in there. But at the end of the day, it boils down to what's it going to cost to build the system. If putting in 2 U-tubes is going to add $3 a foot to the cost of building a system, it might be better to put in a single YouTube and do a bit more drilling. But you've got to look at talking to the contractors that are going to be putting these systems in. A lot of guys ain't going to like putting in 2 YouTubes into a borehole. So you have to look at. There's a bunch of things you need to look at. What I've touched on today basically is where our starting point is, the building and the mechanical system. There's a whole lot. There are things you can do on how you select the what type of ground heat exchanger to install, the detailed design on that to make sure that you can that can be installed properly and that the air can be flushed from the system, that kind of thing. But the biggest, where you can have the biggest impact is right here. That's where we spend the bulk of our time in the whole design process. Any other further questions or? Okay, I'll be around for a bit yet. If anybody has any further questions or if you have any comments, I can do that on the chat feature.
Thanks, Ed. Nice
okay. Thanks. Appreciate it.
Thanks, Ed.
Yeah, thank you.